classification problem. So in that case, we have each input data set here, we might have multiple classes, multiple categories that we need to choose from. And that will be in general the multi-class classification problem. And we already talked about the approaches of multi-class classification. So in general, we say we're going to formulate it and also a linear classifier. However, in this case here, because we have multiple classes, and what we need to do is to introduce multiple sets of parameters. And then in particular, we introduce one set of parameters for each individual class. And that will be in this case here. So you have this theta c, this is the vector. This is the vector here, and that will be the same dimension as the input data set x. And we introduce one set of vector for each individual class. C is the number of classes you have. C is the index of individual classes. Well, in the end, how do we make a decision? Well, more or less, we can think about the boundary between two classes here, whether it's a C class or C prime classes here. Once you have this type of parameters here, you can calculate the scores, the inner product between the parameter and the input vector x here. If this score C score is greater than the C prime score, and you say that's class C here, otherwise you say it's class C prime. So that's how do we make decisions here. As a result of that, the decision boundary between any two pairs of class is going to be linear decision boundary, because we look at the difference between these two scores. Essentially, what we look at is whether this C theta C minus theta C prime dot x here is whether this guy is positive or not. Right, so we have dot product between these two here. So as a result, you can see that the decision boundary will be a linear decision boundary, and with a plane with normal vector. This is the normal vector of the plane. And then, but itself will be linear decision boundary. As a result of that, you can see that we might have get a decision boundary look something like this. So in this example here is two-dimensional data sets, and with three different classes. You might have a decision boundary between this purple and the green here will be this guy here, and this one, and then there's another decision boundary. So each one of the pairwise decision boundary will be linear under this type of models. So, so that's what we talked about last time here. However, now the question is, how do we learn the parameters of these models here? Because now we have essentially a parameter matrix. So how do we learn parameter? And or more specifically, how do we construct a loss function for these parameters here? And that's what we're going to talk about today, and spend time think about what will be the approach to do that. All right, so in order to do that, let's review what we talked about previously, just get the notations right, so that you're familiar with my notations. And then from there, we're going to derive the loss function and derive the learning algorithm to identify the parameters of the models here. So again, we start with the, so we're going to talk about multi-class classification here. So that's today's goal here. So the data here, in our case, we're going to start with data sets here, pairs of x, I, and yi here. So pairs with x is the input, y is the target value. So that I goes from 1 to n. So we have m samples. We assume we have this collections of the training data sets here. So we assume xi here right now is n-dimensional vector, and yi here we assume is categorical. It could be 1, 2, or up to, let's say, we're going to use a K or C here, let's say, pick a C here, represent the number of different classes we have. So a C could be, 3, 4, 5, and then nowadays C can be very large, especially in modern days when people apply the deep learning algorithm here. They want to do object recognition, and then C could be thousands, tens of thousands of that. So that could be actually a very complex problem. So this is the data set we have here. And then the model we talked about so far is this linear model of that. So what do we do here is given input x here, we go through this systems here that calculate the score associated with each individual class. And for that purpose, we're going to use these parameters here. Theta 1 for the first class, x here, so it'll be first score. And then theta 2 will be second parameter for the second classes here, and so on. So overall, we have theta c here times x here. So this is the inner product between these two vectors. So these are called scores, linear response scores given a particular input. And then the parameters here would be my theta here. Be theta 1, theta 2, and up to theta c. C is the number of classes here. For instance, it could be minus, say c equal to 10. Just keep it, one example here. So you say c equal to 10, that would be 10 class classification problem. So this would be theta here. So because each individual theta I here is n-dimensional vector, sometimes people represent theta here with this big matrix. So if you put the theta 1 to be the first row of that matrix here, and then there's theta 2 to be the second row of this matrix, and theta c to be the last row of this matrix here, and you get a parameter matrix here, and that essentially contains all the unknown parameter that we want to estimate from the training data sets. So this C matrix here, the parameter matrix will be a dimension of a C by N matrix. Because you have C different columns, C different rows, and N different columns. N will be the same as the input dimensions here. So this is a parameter. But by doing that, what do we calculate is this is scores here. So what are we talking? So we have this as the first score, this is the second score here, and that will be the last score. And then what we did next time is a very important step. Given the score here, we want to calculate a probability of assign class labels to this data set here. And we have 10 of them here. But what we did here, we would like this probability to be somewhat proportional to these scores here. So what I mean proportional means that with the higher score, I will assign a higher probability. However, because the scores here can be positive, can also be negative. So if I need to convert this to a proper probability distribution. For that purpose, I need to make it a positive. The second thing, I want to make sure that the probability score is between 0 and 1. So I need to do a transformation to reach that goal. The transformation I did last time is introduce operation, something called Softmax operation. Let's go through the Softmax operation. So Softmax receives the scores S1, S2, SC as the input and produce this probability stuff here. And that would be these guys here would be exponential S1 divided by this normalization constant here. And so that constant is I'm going to do use a notation here. That will be let me change notation here. So I use the same notation that I did last time here. I use this is K here. So I use K, big K here, K different classes here. Different classes here. So bigger K represents the number of classes. So I make my job easier. So here, so what I'm going to do, I'll convert to this exponential of S1 divided by a constant. And then the second one will be exponential of S2 divided by a constant. And last one will be exponential of the SK divided by a constant here. And this, this is the new meanings of that. The C here, this C here is a normalization constant. And in particular, C is simply equal to ES1 plus ES2 plus ESK. So this is the normalization constant. By doing that, and you can see that each one of those components here now have values between 0 and 1. And also they're positive because you take an exponential of that. So Softmax, you can see, serve these functions here, receive the input of the scores as the input here, produce this kind of the scores here can be interpreted as a probability distribution. In fact, we're going to interpret that way. We're going to say this guy here is the probability of sign y equal to 1 given your data set here. And the second one you say is the probability of y equal to 2, class level 2 given x here, and so on. Probability of y equal to k given x here. So we have this type of probability kind of out predictions here. And that's something we're going to work with here. So in particular, I'm going to call these guys here, call it my y hat. This is my prediction. So my prediction from this models here is going to be a vector that contains the probability assignment associated with each individual class of that. So that's my y hat associated with this multi-class classification models. So let's rewrite that again, summarize it. So what do we talk about now? So we have the models here. So given x here, I apply the scoring functions here. I get the scores of that. I get S1, S2, and SK. So you get a column vector of that. And I apply Softmax. So by doing that, I get my y hat. So y hat itself now is going to be probability associated with each individual classes. So this is my predicted probability of assigning each individual classes here. And in particular, py equal to 1 given x here. So that is a y hat. The first component of that will be this guys here. The first component of this guys here is simply the softmax ES1 divided by a constant. So if I want to write down S1 here, it's essentially E theta 1 dot x here divided by a constant here. So that will be the probability assignment of the first class. And you can similarly write down the probability of assigning all individual classes here. So that will be the last one with the probability of assigning y equal to k given x here. So that will be exponential of the last score divided by c. That will be exponential of theta k dot x divided by c. So you can see that by doing that, I will be able to make predictions and give meanings in terms of probability distributions of the scores here. So that's my models here. So this models here is good because not only you're able to make a prediction. Well, in the end, if you want to make a prediction here, you check all this y hat here to see which class. So see which the predicted classes here. So find our predicted class label. And that would be simply say, you can do argmax here, go over all the index here to see which one give you the largest probability distributions. And so that does make sense because say, well, I'm going to assign label associated with the highest probability. And the high probability is the most reasonable. And to make that assign class label to that one. But that will be equivalent to say, what's the argmax here over all the class labels, such that that one gives the largest scores. So that's the same thing here. So I'll go over all the parameters here. I'll calculate the score to see which one gives me the largest score, and I'm going to assign class label to be the corresponding index of that. So that's all similar. So you can see the way I introduce the softmax operations here. So this operator does not affect my final predicted labels. I don't need that because for predicting label purpose here, I just need to calculate these scores here. However, the softmax is nice because give me a probability interpretations of these probabilities here. Because once I assign labels here, I can check these absolute values of this y sub k here. And I might be saying, well, how confident is this prediction? Well, if y hat, this optimal index is 0.9, and then I will be very confident to call that class label. On the other hand, if my class label is y hat is 0.3, even though 0.3 is higher than all the other probabilities, but it's not high enough. So for that reason, I might say, well, even though I'm forced to make a decision here, but I'm not so confident to call that class label. You can see this scores here is kind of different. So in that sense, essentially, what's the gap between the scores, the largest score, and then the second largest scores? And the gap here provides you a confidence measure in terms of assigning the labels of that. The larger the gap, the more confident you are. If the gap is small, essentially there's not much difference. So you can see the difference between them here. All right, so this is the predict class levels here. So that's all good. In this case here, I have this theta 1, theta 2, and up to theta k are parameters of my models here. The question is, how do I identify those parameters? And what can I do that? Well, for that purpose here, and then the next question is this: what is our loss function? So what is our loss function here? So now there are multiple ways to address these questions here, and different algorithms can give you different loss function. So today I'm going to talk about this kind of negative likelihood based on loss function. And in the future, I'm going to introduce other type of loss function. But today I'm going to stick with this probabilistic interpretation, giving you a kind of very natural definition of loss function based on the so-called likelihood calculation. All right, so that's what I'm going to do here. So for that purpose here, I'm going to stick with this interpretation, the probability interpretation. So for that purpose here, I'm going to consider one sample. Consider one sample. Just like in the case of the binary classification, you have y, x here. So this is one sample, the x is the input, y is the corresponding labels here. So y is known, and if within the training data set. So y, which means y could be 1 or 2 or 10. So now I want to say, well, so given x here, so this is my training data sets here. And the first one I'm going to do, I'm going to run prediction on this input data sets here. I'm going to prediction is this. So prediction is this, is y hat from my model. So I will be able to calculate the probability of assigning class label to each individual classes. And that's my prediction, because I assume I know some parameters associated with this prediction here. So that prediction here is this. Let me rewrite that again. So it's the probability of, what is the chance of probability of assigning class 1 to that data set, given that particular data set x here? And what's the probability of assigning class 2 given that particular data set, and so on. So I have this vector that contains all the information I want to know regarding sign probability, the probability of assigning individual class. This is, I can calculate from my model. So this is known given the parameter. Given the parameter here. If you know the parameters, I will be able to calculate that. Okay. So I should not say it's known here. What can be calculated? Can be calculated. Given theta, given big theta matrix. So I can calculate that quantity. All right. So the question is, I want to check how, I want to verify next to this. I want to check the consistency, right? How, consistency between my prediction, y hat, and the actual class label y. So there are two numbers here. So, and don't confuse them here. So this guys here right now is the real class label assignment from your training data sets. We can view that as a ground truth labels. Y hat here, on the other hand, is the predicted probabilities from my models here. And this guys here is a vector. Y hat is a vector. Y is now, right now, is a scalar, is an integer from 1 to C, to K here, 1 to 10 here. And I want to check how consistent they are. Well, so what I can do here, I can look at all the possibilities here. So one possibility here, suppose let's say if y is equal to 1. So if y equal to 1, what happens? So if y equal to 1, so if the ground truth label is 1, well, what should I do? Well, I check, I'm going to verify what's the likelihood. What's the likelihood of assign label 1 to x here. So that's what I'm going to check here. Well, likelihood now is calculated based on the first component of this guy's here. That is this probability of y equal to 1 given the x here. That's the likelihood according to my models here. But similarly, well, let's do the other one here. What happens if y equal to 2 here? And then the likelihood here, likelihood of assigning this 2 to x here, is going to be probability of y equal to 2 given x here. And so you can see the likelihood of that. So the likelihood, we would like, so if the ground truth is 1 here, I would like to see this number is higher the better. The higher the better, because the higher the likelihood, which means your model is doing the right job, doing the correct predictions. Because otherwise it would be wrong prediction. So as a result, I would like the likelihood to be high. So, and that would be follow the similar logic what I did last time here. So what I'm going to do here is, and now we're going to first of all take a log of this likelihood function here. So that doesn't change the direction of that. The higher the log of likelihood, it is better. So that's the same thing here. And then we're going to convert that into a loss function. And for the purpose of constructing the loss function here, I'm going to take a negative sign in front of that. And now because negative sign in front of that, I want this negative log likelihood the lower the better. And that will be consistent with my overall formulation of minimizing the loss function. So that's what I'm going to do here. All right. Essentially now, what I'm going to do here, essentially, I'm almost done here, essentially saying this. What will be a good loss function for these samples here? What I'm going to do in this one here is saying this, I'm going to check what is the actual labels of this y here. If it's 1, I'm going to use in this one as my loss function. If it's 2, I'm going to use this guy here as my loss function. So and so on. So I have this kind of a if kind of logical statement to tell me which term should I use to construct my loss function. So which means I can rewrite them into this way, into this formula here. Say my loss now is this guy's here. A loss for one sample for x and y here. So that will be loss here is going to be equal to one of the possibilities here. If y is equal to 1, so this will be my log probability of y hat 1 here. So that will be my loss here, which means this is equal to my negative log here. Remember that will be theta 1 dot x here. Will be log of exponential theta 1 dot x here divided by constant here. So that's my negative log likelihood here. Negative log likelihood formulation of that. And if you want to rewrite this guys here, it will be equal to minus theta 1x here. You can see that because log of the exponentials here. And the next would be plus log of the constant terms of that. Constant term. And the constant term is this normalization constant of that. So that's the log likelihood if y actual target level is 1. And you can write all of them here. And if the actual target level is 2, and you're going to use these terms here instead of using the second term here, and that will be minus log of the exponential theta 2 times x here divided by constant. And that will be minus theta 2 dot x here and a plus log of constant here. And so you can write all of them here. Y to c, that will be negative log of y c hat. Okay, and that will be equal to negative c dot x here plus log of that constant. Right? So that's my loss function here. And right now, in order to calculate the loss function here, I just need to pick up one of the terms here. Either this one or this one or this one. It depends on the actual class label that I have. And that's how do I construct the loss functions of that. All right? So that's pretty much it. This is called a negative log likelihood. And sometimes people call it cross-entropy. Cross-entropy loss for the multi-class classification problems here. And I have to use this calculation to do that. So what I'm going to do next here, I'm going to propose a new notation to somewhat kind of make this notation slightly easier. So right now, this notation here is correct, but it's not very easy to write down because I need to use this if statement and to verify what the target, and then I'm going to plug in corresponding probability to that. And so you can see, it's not very concise to write down that. So, however, I'm going to use a new notation, and the new notation will simplify the notation. Not only simplify notation, it will simplify some of the understanding of this term, this meanings of this loss function a little bit as well. So the new notation is this. So I'm going to use a notation here to denote the class labels. New notation, okay? So right now the class, ground truth class label here, y here is an integer representation of the 1, 2, or a number C here. The C is the number of classes. I need to make predictions. So it's an integer representation. So what I'm going to do here is this. I'm going to convert that into a vector representation. So what I mean is this. So I'm going to represent 1. If y is equal to 1, I'm going to represent with a vector here. Vector to be, so this is a y here equal to 1. And then the new representation, I'm going to represent as a binary vectors here. To be first component to be 1 here, and the rest of them are 0. So this is a new vector representation, and in this vector representation here, it's a C-dimensional. So RC here. So if C is a 10 here, that would be 10-dimensional vector, which means you have 10 different components. Essentially, I'm going to indicate that which component is associated with the corresponding class label here. Well, if class label is 1, I'm going to put the first component to be 1. If class label is 2 here, what I'm going to do, I'm going to put the second component to be 1 and rest of them to be 0. So, and so on. So if C is equal to last class here, and I have all zeros here, except the last component is not 0, is 1 here. You can see now, there's a 1-to-1 correspondence between these two representations here. And the only difference here is this. I'm going to use these guys here are binary vectors. Binary vectors with only one component, with only one entry being 1. Okay, so precisely in these vectors here, all entries are 0 except one entries are 1. And these are called one-hot representation. One-hot representation of the class labels. This is a kind of equivalent representation of the class labels, and it sounds like more complicated way because previously I can represent those with just one number here, but now you have to represent with 10 different numbers for that. It sounds like complicated, but it's actually more convenient for reasons I'm going to show you next here. Right, so this is called a one-hot representation. From now on, most of the time, we're going to actually stick with the one-hot representation instead of the original class labels of that. And for the reasons I'm going to talk about next year. All right, so for now, let's assume I'm going to represent those class labels here using this kind of one-hot representation instead of the integer representations. If I do that, okay, let's look at back here. If I do that, let's say I'm going to use this one here under one-hot representation. Representation of y. Suppose y now is a one-hot representation. And then in that case, I can write down loss to be simply equal to minus y dot log of y hat. So the inner product between the y and the log of y hat. Let's think about why this is the case. Well, if your class label is 1 here, and which means on the one-hot representation here, y now is a vector with first component is 1 or rest of the component is 0. So now if I take it in the product between these two vectors here, only the first entry survives. All rest of the entries are zeros. That's exactly this component here. Similarly, a logic applied to the second component here because only second entries are 1 all rest of the entries are zeros. You can see this exactly the same as the loss function here. But by doing that, I do not need to use this if statement here. And that itself is kind of very concise way to represent this loss function here. So under this representation here, is keeping in mind here, y now is n-dimensional vector, n-dimensional binary vector, right? One-hot representation. And y hat here is also n-dimensional vector here, but it's not binary. It's a probability vector, which means that its entries are between 0 and 1. So not 1 or 0, but between 0 and 1. This is a probability vector. And these guys here are exactly 0 or 1. Y hat here, in fact, if you look at the softmax functions here, y hat will not be exactly 0, never be exactly 0 or 1 here. It's always going to be a number between 0 and 1. So you can see those two things, but the good thing, the dimension matches here. So that's the reason I take the kind of dot product between them here. Or you can write down them into a matrix representations here to be simply saying this is equal to my y transpose log of y hat. So by doing that, I'll do the same thing, but I'm going to use a linear algebra notations of that. So that's the loss function for one sample, here. And now with that, I can calculate the overall loss function for all samples I have here. And that will be final loss functions here. That will be functions of all the parameters I have here, theta 1, theta 2, and the theta c here. Remember that I have a c different vector. So what I'm going to do here, I'm going to go over all the samples here, take an average of the samples of that. And then each one of them loss function here will be negative. The class labels of that samples here will be j under one hot representation. So these guys become vectors here. Adopt this log of y predict the probability for the j samples. And that will be my overall loss function for the entire collection of the training data sets I have here. So very kind of concisely written in this way. So that's the negative log likelihood or cross-entropy loss. For the multi-class classification problem. So the next question, obviously, naturally, we're going to continue to solve the learning problem. So learning again, so what we're going to do, we're going to find the parameters that minimizes my loss function. So we're going to minimize over all choice of the parameters here. So remember now, you can theta 1, theta 2, and theta c here, also parameters here. That's the entire loss function. So that's what I'm going to do next. So before I doing that, there's a notation wise, you can also make things more compact here. So what you can do is this. You remember theta here, I use this, you can represent it with a matrix here. So by doing that, and you can think about it, if you're doing this guys here, and then what is the theta times x here? Well, that will be the scores. There will be a vector of the scores here. It will be S1, S2, and SK here. So that will be scores of that. And now you can think about it here. If I apply a softmax to theta x here, and that will be my predicted probability. You can write down those things more compactly in this way. But when you write that, you assume this guy here is now in the matrix. The theta here is the matrix here. Just keep in mind that that's the case. And this is the more kind of softmax representations of this probability in this way here. All right. So that I want to mention that sometimes people write down in this way because by assuming theta is a matrix, you can make things more compact this way here. All right. So that's the notation wise. But now let's go back to this question here. How do we solve these problems? Well, for that problems, we know how to solve it, right? In general, we know a general methodology for doing that. What the methodology you're going to use gradient descent method. Gradient-based methodology. And for that purpose, we need to calculate the gradient of that loss function with respect to each individual parameters here. And that's what we calculate here. And the question, how do we calculate this quantity? So now this quantity here will be, so let's consider the loss for one samples. So suppose I'm going to consider only y and x and y here. And how do I calculate the gradient of this respect to each individual theta parameter? Well, let's do simple things here. Let's say consider the calculate probability respect the first parameters here, first set of vectors here. How do I calculate this quantity? Well, so now the loss function here will be these guys here. Will be y dot log of this log of the softmax of theta dot x here. And that's, if you want to write that down, that would be this guys here. You want to calculate the probability of that. And within the softmax, this guy's here. Softmax predictions here. And essentially this is my y hat here. And that's equal to a vectors of this guys here. And first of all will be this guys here. Will be theta 1 linear term times x. And then you have log of that constant here. Theta 2 dot x here, and the log of that constant, and so on. Right. So, well, if you look at this function here, you're going to apply chain rule to this function here, to overall this function here. Well, first of all, you apply to the log function, and then you apply to the softmax function. Essentially, apply each individual component of that, and apply them with respect to theta here. Well, for these guys here, respect to theta 1, that's easy, and that's simply x here, right? And you might think that's very easy here because I consider a log function here, and then only consider this guy here. However, the thing is slightly more complicated. The reason is this: you have this log of c here. What is log of c? Well, if you look at here, log of c here essentially is log of exponential e theta 1x plus exponential e theta 2x here plus exponential e theta kx here. And then take a log of that. And you can see the constant here actually is a function of the parameters you have here. If you look at that, it's a function of the parameters I have. So, so as a result here, the gradient of this guys here with respect to theta is not 0, because you have to consider evaluate the corresponding dependence of theta within the log of the exponential terms of that. So as a result, you have to carry out this evaluation of the gradient with respect to log c here. However, that's doable. That's doable here. And I will not do it here, but I will encourage you to try it out when you have time at home and to calculate what is exactly the gradient. If you do that, it turns out that the gradient of this guy here turns out to be, you have very simple forms. I'm going to write down that simple form and then try to see if this makes sense or not, okay? The gradient, if you carry out this calculations, and the loss function here of one samples here with respect to theta 1, the first set of parameters here is simply equal to two terms, product of two terms, and we kind of talk about that again and again. So this term here is going to be 1 hat minus y here. 1 hat minus y. So what is 1 hat minus y? You think about that. So that is 1 times 1, the subscript 1 here times subscript 1 here. Essentially, for the first class level here, what is the difference between prediction and the actual class label assignment of that? So essentially, you can treat this as a residual, and then times the x here in this forms. Very simple that. So in fact, you can generalize. So this is theta 1 here. In fact, you can generalize them to be any arbitrary index here, to be say theta k here. That would be the k's predicted probability and the k's ground labels of that, and times x. But now it just interpret this guys here is the residual, the error. Or you can think about it as a residual. So that says for that case class, and this is the predicted probabilities here, and y sub k is this ground truth notations here. So in this case here, y sub k here, remember that is a binary number now. It's either 0 or 1. So if your actual target label is exactly corresponding to be equal to k, and then yk will be 1. Otherwise, y sub k will be 0. So this is in a one-hot representation, right? And then x here is the sensitivity parameter. Okay, so by doing that, you can see this, right? The formula here is almost identical to the gradient calculation we have done for the linear regression, and also we have done for the logistical regression for the binary classification case. If you recall that for binary classification case, this is the same thing here, right? In that case, y sub k is a binary number, 1 or 0, and y hat is predicted probability, and that will be same as in this case here. And then times this x here, sensitivity parameter. You can see, you know, this formula appears, this generically appear again and again here. So, so this goes back to even within the neural nets. In many cases, you can see that that turns out to be in similar forms as well. So the gradient is always the product between two terms. One is the input you receive to that unit here, and then the y hat minus y is this residual or error term. So you can see now appears in this case here. Later on, you'll see that appears in the framework within the neural nets as well. All right, so that is the gradient calculation. So I didn't prove that, but you can see in the end, the formula is pretty clean here. And let's see whether this makes sense or not. Let's look at that here. Let's look at here. So let's do some simple logic calculations here. Well, so let's look at it here. Let's suppose here, whether this makes sense or not. Let's for the sake of the discussion, let's suppose x or positive, which means our input are positive here. So now let's think about here. Suppose your labels here equal to 2 here. Suppose your ground truth label equal to 2, which means, you know, y is going to represent these vectors here. Equivalent representation in one hot will be 0, 1, 0, and where is only second entry is 0, is 1 and 0 here. Well, now let's look at it here. Let's look, how do I update this parameter theta 2? Let's look at, for the sake of discussion, let's do that. Well, so now it depends on your predicted probability of sign class level 2 here. So if this guy here is very far away from the one here, very, very small. If it's very small here, this residual turns out to be very negative. Okay? Because it's very negative here, which means what you're going to do is you're going to take update of the parameter here in the opposite direction of that, which means the direction of change here will be very positive numbers here. You need to increase the value of the parameter. So once you increase the value of theta 2 combined with x here, you'll boost up the values of the score. And you can see that by doing that, you're trying to match these probabilities and so on. So you can see that this logic here does make sense. It's very similar to the logistic regression part of them. All right, so this is for the gradient calculation for the parameter theta here. So, so you can write that for each individual index here. And there's also another more compact representations here in terms of the loss function here. So right now, let's rewrite what we talked about here. This is a loss for one samples here. For that particular theta k here, we say that I have to look at these predicted probability for the case classes here, minus the actual observations of that under one hot representation times x here. And that's k goes from 1, 2, and 2 different classes. That's one way we'll represent this guys here. Alternatively, you can represent this loss here in terms of the matrix, the x and y here, with respect to entire parameter matrix here. So then now this guy here is going to be a C by N matrix. Because you're going to calculate this loss function with respect to each individual component of that parameters here. And how do you represent in that case? You can simply represent to be something like this guy here. To be y hat minus y times the x transpose, simply like that. So let's look at what this means here. Well, in this representation, because remember that now the left-hand side has to be a matrix, this gradient matrix here. You're going to calculate loss with respect to each individual component of that parameter matrix. And let's look at the right-hand side, that to be a matrix, right? So indeed, that's going to be a matrix here. The way I do matrix here is going to be the outer product between these two vectors here. Between these two vectors here. So one is this guy here is n-dimensional. No, sorry, it's k-dimensional here. And this guy here, x here is n-dimensional. But you're going to transpose that, make it to be a row vector. So you're going to take the product between a column vector and a row vectors here. So that itself will lead to a k by n matrix. So you can see the consistent. So that would be much more compact representation of the gradient. And then because once you do this guys here, and then you can so now this is for one sample of that. So you aggregate another samples for loss function for all samples of that. I'm going to use this big theta notations here. And then that will be average over all examples you have. And that will be y predicted jth sample minus yj sample of that. It's a prediction between them. That will be the jth sample out input of that, take transfer of this guys here. And that will be the probability from one sample, you average them. That's the gradient over the entire collection of the samples here. And once you have these guys, and you know how to update your parameter matrix here to be simply theta here minus alpha times the gradient of the L respect this big theta matrix here. And that will be the gradient descent step. Update rules here for updating the parameter. And then if you're using this notation here, you can update the parameter using this one formula for doing it. You can see that's very convenient purpose for using this matrix representation. So that is the parameters of the kind of multi-class classification here. So this one is very generic here because the reason nowadays, and later on when you extend in many applications, most of the real world application here is that in fact there are multi-class classification problems. You have to choose from one out of k different categories of that. So by doing that, you will be able to handle by doing this one here. Okay. So a few other comments. I just want to make comments here. And then we're going to apply gradient descent to this loss function here. And then very naturally, you may ask me here, so what is this loss function looks like here? This loss function, we wrote now in this part here. Where is my loss function? This is my loss functions here, right? So in this loss function here, and I mentioned that gradient descent algorithm can only guarantee to identify a locally optimal solutions. And for this type of function here, what about this forms of that? And then we mentioned something called a convexity of a function. And for both MSE loss function under linear regression and also the binary cross-entropy, that is a negative log likelihood function for the binary classification problem. We said that both of these type of loss functions are convex. And as a result that if you apply gradient descent here, you're guaranteed to find the solutions. The same thing is true for this type of a loss function here. So this is also a convex function with respect to these parameters here. If you apply that, you'll be able to identify a global optimal solutions. However, just one thing I want to mention here, those parameters here are redundant. So which means, and that there are some shift of these parameters here, what does not change any solutions or any classification decision process, but the parameters here, you can shift around. So why this is the case? Well, let's look at it here. Let's look at this part here. So in the cross-entropy terms here, in the Softmax calculations here, if you look at the Softmax calculation here, it's going to be exponentials of the score here divided by a constant function. If you look at it here. So what does it mean? Let's write down the Softmax calculations. And you can see that why the parameter theta are not unique. There's a redundancy within that. So let's look at this guys here. Softmax of this score here, theta 1x1, theta 2x here, theta n, theta k dot x here, and this is equal to exponential of theta 1 dot x here divided by the constant. Let's look at the first terms now. You have all the terms. Let's look at only the first one. Exponential theta 1 dot x here times exponential theta 2 dot x. Exponential theta k dot x here. So now you can think about it here. Let's say I'm going to change theta here. I'm going to change theta 1 to be new theta 1 here, to be theta 1 minus theta 0. Shift by a constant here, constant vector, any constant vector. And theta 2 to be updated to be theta 2 minus a constant vector, theta 0. And so on. If I do that, so what happens? If you do that, you can see that this new theta here, if you plug into this guys here, will not change the softmax function, the output of the softmax function. Because if you do shift on the theta here, and then if you shift with the same terms here, the denominator and the numerator can be canceled by the same constant terms. So as a result of that, if you shift those values by a constant, does not change the result of the softmax function. Consequently, will not change the predicted probabilities. So hence will not change anything else. Right? Will not change the loss function, will not change predictions. So if you think about this way, if you apply gradient descent to this guys here without fixing constraints here, you're going to run into the problem here in that every time the learning here might be returning you slightly different result with shifted values from one to each other. For this reason here, there are multiple ways for fixing this. So one way of fixing this guys here is this. You might want to, so make anchor one of the values here, maybe anchor one of the theta 1 here to be a constant vector to something so that it doesn't, you don't need to shift that anymore. So you say, well, theta 1 is simply equal to be a constant or divided by that. So you can say, well, once I get this guy here, I want to make sure that my first predict probability is always a constant number. And then the rest of it is you can rescale by that. So which means this, what you can do, in fact, you don't need to choose the theta 1 here. You only need to choose theta 2 and theta 3 and up to theta k here. Essentially, you get rid of that. Get one set of parameters here. And by doing that, you said the first term, exponential terms here is 1, and next is theta 2 times x here. And the last one is theta k times x here. You get this vector, and then properly normalize this vector here and get the probability distribution of that. So that's one way of doing that, but you don't have to do that. So in fact, in the algorithm here, usually when you implement the softmax function, you have to be very careful because you're taking exponential of these guys here. You do not want this guy's sphere to be too large. And if it's too large, and then that would be number is going to explode because after you take exponential of the large number, that can be extremely large number. So you have to be very careful when you implement the softmax function. But however, this is just an implementation details. I just want to mention that. Okay. All right. So those are the discussion of the multi-class classification. As you can imagine, if you use this algorithm here, you will be train a model for multi-class classifications. All right. Let's summarize what we talked about so far. So we talked about how do we solve multilinear classification problems. And the way we're doing that, we formulate a loss function. That would be cross-entropy loss. By doing that, I will be learning the parameters of the models. So that sometimes this type of model I mentioned here, and people call it multi-logit regression. So that just as kind of extensions of this logistic regression, right? And then you can think about it as a multi-logit regression here. But nowadays, people simply call it softmax and multi-class classification, and now what it means. And by doing that, what you can calculate the loss function I talked about here, and then you get decision boundary to be piecewise linear decision boundary between any pairwise comparison of that. In particular, I want to mention here, this loss function is a convex loss function. So as a result, you can solve this problem, derive globally optimal solutions to that. So that completed our discussion of the multi-class classification. And I think I'm also done with this kind of in the simple linear classifier here. I talked about perceptrons, I talked about binary classification, and by doing that, I introduced this kind of a loss function so that you can derive gradient algorithm based on this loss function. So that can be applied to a generalized or multi-class classification. So next, I just want to mention a few items here. So this item we already mentioned for the regression problems, and that can be similarly applied to the classification problem here. So for that reason, I'm just going to go through them very quickly. So for instance, one thing is this. So again, just similar to the linear regression problem here, even though we talk about linear classification here, it does not mean the model is restrictively linear. So what we can do in order to generate nonlinear decision boundary, we can augment features, generate new sets of features by using nonlinear transformations of the input here, using, for instance, polynomial functions or radial basis functions, or sinusoid or other types of functions. So by doing that, you can generate nonlinear decision boundary. But however, the parameter you learn here is still going to essentially you're going to extend to utilize new sets of parameters associated with these new features here. The function is still going to be linear functions of the parameters here. So by doing that, you can increase the complexity of your models by introducing new features here. And the question is, and then to what extent you want to know whether your model is overfitting your data set or not. So there are multiple techniques for doing that. We mentioned that for the linear regression. One way you can do it, you can do cross-validation procedures for doing that. So alternatively, you can use regularization techniques to control the complexity of the models. So that would be very similar for the linear regression models of that. So what do we do here? So in addition to the loss function here, for instance, within the context of the logistic regression here, you have this binary cross-entropy loss. You remember that? This is a binary negative log likelihood functions here. And then you can add one more regularization terms to the loss functions of that. So regularization term encourages you to make the parameters smaller, because when you minimize this overall loss function here, you don't only need to minimize so-called data terms here. This is usually called a data term. It's called data term. And this second term will be regularized. Regularization term. And alpha here is this regularization parameter. And then this is something you have to choose. And it typically is a scalar, positive scalar. So, and then essentially the weight parameter balancing the need to reduce the data term loss and the regularization terms of that. So in general, if you choose alpha to be relatively high, it will focus you, make sure that these norms of the parameter theta to be small. And then we talk about norm here can be any arbitrary norm. And then in general, that can be a p norms here. That would be valid norm as long as this p is greater or equal than 1, right? So, and in that case, you have a proper norm function. So that would be defined to be these guys here. This is so-called p norm. So in many cases here, people even go beyond the norm, choosing something less than 1. So you have something like, look like this very kind of strange shape of that. Under this case here, this guy here is not a proper norm anymore. And however, you can still use it, even though not proper norm. For instance, this guy here is not convex anymore. If you can verify, you can see easily see that. Not convex anymore. And remember that to measure to convexity, say you draw 2 lines here, whether that line is always above the graph. And now you can see this is not the case. If I draw a line here, this line is actually below this graph here, below the curve here. So you can see this is not a convex, but all the rest of them is convex. So in general, the function will be convex as long as it's a proper norm, which means will be convex as long as p is greater or equal than 1. So this is, people don't use it very often here. Mostly use it either p equal to 2 or p equal to 1. So p, and also we mentioned that when p equal to 1 or 2 here, that usually give you 2 different behaviors. This is associated with a quadratic function. This is a function here. This is so-called the unit ball of that. Essentially, this is the surface where the norm is equal to 1. You can see that. And if you use p norm, the regions that norm equal to 1 will be exactly a circle. It's called isosurface. And the isosurface for the p equal to 1 norm would be this diamond shape here. And in fact, we have these corners of that. And these corners make this function non-smooth. As a result of that, what happens is that your parameter will tend to reach those boundaries of that. And this is not the case for the L2 norms when your isosurface is a circle here, and your reach point here, theta here, and and then the higher the regularization parameter, you push those things toward the origin, 0 points of that. But you will touch a point. And however, in the case that you're using an L1 norm here, in many cases you touch the corners of this kind of isosurface. And the corners, which means that some of the components will be exactly 0. And that's many cases people like this type of behavior because this tells you immediately which features are finally selected for making the classification decisions. And if the parameters here are 0, which means that those corresponding features does not participate in this decision process, you may well just throw away these features, right? And for this reasons here, this approach here is a very nice approach for performing the variable selection or feature selection. It's a term people use in this community here. Feature selection or variable selection. So what this means that I'm going to choose a subset of features and use that as an input to my models here. And then initially, you don't know which one to choose, which one to not use. However, if you apply this L1 norm-based regularization, if you run that, if the corresponding index parameter is 0, in that case, we say the 1 is 0. So you can throw away the first features of that. And in general, throw away features corresponding to the theta coefficient are zeros. So, and then how to optimize this ones here, and then you can apply a gradient-based methodology to optimize this case here. So in general, if this L1 here is the L2 functions here, and then that's a smooth, you can calculate gradient very easily. But if it's the L1 norm on the left side here, and then there's a little bit non-differentiable point here, and that can make the algorithm create some of the problems for this algorithm here. So people have a better efficient algorithm for learning the parameters of the models here. And this type of classification problem is something called lasso here, if you use this type of regularizations. And with lasso regressions here, sometimes there are sometimes a more efficient algorithm to solve the optimization problem instead of this simple gradient descent-based algorithm here, because this one here, the gradient does not exist. So that's what I want to say regarding this binary classification problems here. And this shows you actually very nice pictures and tells you when you change the regularization parameters here, and to see how the coefficients, the theta parameter corresponding different features changes. And this is an interesting observation here, very nice. And then so in this side here, and this is a L2 based regularizations here. And then this is a regularization parameter. Remember the regularization parameters here. So and this is actually 1 over regularization parameter. So when regularization parameter is very large, so that would be the left side of that. So in that case, you're going to force all the parameters to be zeros. Okay. When you're on the right-hand side of that, essentially regularization parameter is very small. Essentially, it's close to 0. You can think about it. There's no regularization applied to this classification problem. So this problem is data sets. We have the data set. You're welcome to try this data sets here. You try to predict based on set of features here. This is essentially a few tests. This is from diagnosis test here. There are a few of the different tests here. And then in the end, you want to make a prediction whether the patient has a diagnosed, has a prostate cancer or not, based on those so-called biomarkers. And you have 1, 2, 3, 4, 5, 6, 7, 8 biomarkers here. And then and this is diagram shows you when you vary changes this regularization parameters here, how those the coefficient, the theta, correspond to different feature changes. So in this case here, there's no regularization. So you can see that, and you have multiple features, and then the coefficients associated with all the features here are non-zeros, right? So they are relatively large here. Now, if you increase these regularization parameters from the right to left here, you can see that it forces you make the parameters smaller and smaller, and to a certain extent, then make all of them to be zero. And essentially saying that, well, because you have imposed a very strong penalty on the magnitude of this parameter. So as a result, you will make them to be small. So this is an L2 based on regularization. Right-hand side here shows you the behaviors of L1 norm-based regularization. So similar, so there's no regularization. This is a very strong regularization. And now you can see if you vary this regularization parameter from no regularization to make it to be stronger, make it increase the parameters, the alpha from right to side here. So initially you have all the parameter and you learn the coefficient of that. And then now you can see what happens here. After a certain point here, and then there's one parameter one feature will drop. When your regularization reaches this point here, and these features here, this is a feature corresponding to the Gleason here. You can see this Gleason features here will drop right away. And the first feature drop is Gleason. Essentially, among those features here, Gleason is the least important one. So you can remove that. And now in this case here, because the parameter is exactly zero. And after that, and now you verify again to see which one drop next. You can see the red ones drop next here. This will be another set of feature will drop after this guy is here. That red one is the age. So say age is the second least important factor of that. If you keep moving here, that would be the blue here. That would be, I don't know which one is talked about here, one of them here. And the next will be green feature, will be the purple feature, last this feature. So this feature is the most important feature because this is the least feature that drop out from this algorithm here. And this type of diagram here is sometimes very useful because it tells you when you vary changes the regularization parameters here and see the more or less give you a rank of the importance of different features in this particular problem there. And for this reason, many people call them so-called regularization paths of this algorithm here. When you vary this regularization from the strong to left here, to see how these different features drop off from these models. Right. So that's in many cases it's very useful things to know. So in reality, right? If you suppose you want to make a prediction here, you have to choose a regularization parameter. Choose one of them. Which one should you choose? Well, then now we'll go back to our generic methodology by using cross-validation. So you can try each one of the regularization parameters here. And once I have the models here, I go test this models here with this choice of the learner parameters on a test data set. And I'm going to choose in this regularization parameter based on the performance on the test data sets. So that would be generic procedure for doing that. All right.